We've been gonna do a solar episode forever, I'm told. Bill and Dylan want to talk a little bit about photovoltaics and how they work, and I will make an attempt at this. Charles Becquerel discovered the photovoltaic effect in 1739 using a selenium plate at age 19 in his father's workshop. No one could explain it for a long time. I guess it was 1839. Albert Einstein was kind of dissed on the Nobel Prize for his theory of general relativity, largely because he was Jewish. It became such an embarrassment at a point that they had to give him a Nobel Prize, and they didn't want to do it for general relativity, so they did it for a 1905 paper where he described how the photovoltaic effect worked and the quantum packet nature of light, which has proven to be essentially correct. Light is has aspects to it as a particle, which he calls a photon, and it has certain aspects to it that are those of a wave, notably in that it has a frequency. Sunlight falls on the earth, in theory, at 1,327 watts of energy per square meter at the Earth's surface. With the attenuation of the atmosphere and some other issues like that, we consider it about 1,150 watts per square meter. And for test purposes, they usually use 1,000 watts per square meter, and that's enough energy to run everything worldwide forever. But we have to convert it to electricity. That's done best, and it has been done various ways, including running steam engines and, to this day, high temperature, high pressure boilers, and so forth. You can feel the energy of the sun as heat on your hand, particularly as we get toward the end of June. So there is energy in this stream of photons from the sun to the earth, and plenty of it. We're kind of into a thing with the electric vehicles, but closely related is this concept of solar. Everyone wants to drive on sunshine, not only cut out the fill up at the gas station, but cut out all the middlemen entirely and collect energy on your own roof from the sun and put it into your car and then use that for your personal transportation needs. And I think that is a tremendously positive aspiration, and if we could encourage that worldwide, the world would be a better place in a lot of ways, in a myriad of ways that I won't go into here. But it starts with the conversion of sunlight to electricity. And let's talk a little bit about how that happened. At Bell Labs, they invented the silicon-based solar cell in 1954, April 12th of 1954, a year before my birth. So we've had them with us most of our lifetime, but in the 60s and 70s, the equivalent adjusted for inflation to be about $100 a watt. I'm told that we're officially at about 68 cents a watt now. And so solar is becoming available to the rest of us and all of us, not just as they were used initially in 1958 aboard a grapefruit size satellite. Today, many people are installing them on their roofs, and therein lies a tale. So how do they work? The silicon solar cell is, of course, based on a silicon crystal. Let's take a look here. I'll put it up on the wall. A silicon atom. Silicon atom has 14 electrons, 14 protons. It's a very balanced thing. The innermost orbital band, the K band, has 2 electrons in orbit. The next band, the M band, has 8. And the outermost band, which on all atoms is referred to as the valence band, it has 4 electrons. Let's talk about this valence band, or the outer shell of an electron. The inner bands, the electrons are held more closely in orbit around the nucleus, kind of like a little solar system. The outermost band is like planets in our solar system, like Pluto and so forth. And if you add energy to an atom and excite it, you typically thermally, but in this case using light, the electrons will pick up that energy, and much as if you had sped up planet Earth around the sun, it would move out in orbit at the outermost or valence band. It'll move out of orbit entirely and go into what's termed the conduction band. It's kind of a gray zone in between atoms where electrons can flow freely. If you knock an electron out of the valence band, it's said to leave a hole. The electron has a negative charge, and the atom lacking the electron has a positive charge. And the flow of electrical current you can view of as the movement of electrons, or you can view it as the movement of holes. You know, we're saying take an electron, knock it out of one atom, and it jumps over to the hole in another atom. Did the hole move from one atom to the next with the electron? Sort of a matter of perspective. But keep that in mind for what we're going to do. Silicon, as I said, has 4 atoms in the outer valence band, but if you notice, the second band has 8 electrons. And in fact, these things kind of come in groups of 2, 4, or 8. The outer valence band actually wants to have 8 electrons, not by electrical charge, but by kind of stability of entropy type thing. It's more stable with 8 electrons in that outer valence band, and so it will accept them. And in fact, it will share them with other atoms. And if you take an oxygen atom and put it in proximity to a silicon atom, they will begin to share outer valence band electrons and become the chemical compound silicon oxide. 2 oxygen atoms, I guess, would be silicon dioxide. Silicon carbide would be a carbon atom, and a silicon atom. If you take nothing but silicon atoms and you kind of process them, usually in the presence of heat, you can grow silicon in its crystalline structure. As I said, each silicon atom has 4 electrons. If it pairs or becomes covalent with 4 other silicon atoms, all of them wind up with 8 in their outer valence band by sharing 1 electron between each of the 2 atoms And so each silicon atom shares with 4 others to get the 8. And that creates a crystalline lattice that is very regular. Silicon, we could say it's a semiconductor. I've heard it referred to as a semiconductor. Of course, we're familiar with glass, which is a crystalline form of silicon, not terribly pure, but it is. And it's an insulator, of course. Everything's pretty much stable. So I don't view it as a semiconductor, actually. It's a good semiconductor base material because it's easy to interject impurities into this silicon crystalline structure. If we took the element boron, it has a very similar atomic structure to silicon, but it has 3 electrons in the outer valence band. And so if we put it into this crystal lattice and let it combine with the silicon, it would become covalent, but it's going to wind up missing an electron. That would be a hole with kind of a positive charge. And we would call that, since it's kind of a positive material, a p-type semiconductor. And that hole will let us move electrons fairly freely through the material, going from hole to hole. And so now we have a semiconductor, a p-type semiconductor. If we took the element phosphorus, which has an atomic structure very much like silicon, except it has 5 electrons in the outer valence band. At that point, we would it would very easily become covalent with the silicon crystal lattice and become a very integral part of that lattice, binding to 4 other silicon atoms. Each phosphorus atom would bind to 4 silicon atoms, but it leaves a remainder, an electron that nobody wants. And so it has a negative charge, and we would call it an N-type negative semiconductor. And indeed, that's how we make a silicon solar cell. The backside, aside from the contacts to pick up electricity, is deposited boron as an impurity, and the front side, the side that faces the sun, is impregnated with phosphorus. And so we have 2 types of semiconductors, a p-type and an n-type, in a very thin sandwich. They've got where they can cut these ingots of silicon crystal into slices that are about 200 microns, or millionths of an inch thick. And so the actual cell is quite fragile. This cell has an anti-reflective coating, the phosphorus silicon, then the boron or p-type silicon. It actually has the contacts sort of woven through it where it doesn't block as much from the front, and they're both on the back, but one set is for the front, or the phosphorus N-type, and one is for the p-type. Where those 2 semiconductors come together, recall that the phosphorus or N-type has a spare electron, and the p-type, or boron doped, and that's what they refer to it as, doping, crystal, has a hole. Would you believe that electron will fit right in that hole, and both the electron and the hole then disappeared? if you have a hole and you have an electron, you put the electron in a hole, you don't have either one, do you? The electron-hole pair has disappeared and you have a fulfilled hole. And if you had that happen a lot at the barrier between the p-type and the n-type, you would soon develop kind of a inert region, a no man's land in between these two materials, where it becomes a little bit like a third material in that all the holes and electrons are filled. And we would call that a depletion region, or a space region there. A depletion region is normally what you refer to it as. If we have a depletion region that has no holes and it has no electrons, it becomes a little bit like an insulator. And we know on a capacitor, if we put a positive charge on one side, like a p-type material, and a negative charge on the other side, an n-type material, and put a dielectric between them, what happens? We develop an electrostatic field. This is like a magnetic field, but it's electrostatic, and it does affect current flow and the movement of electrons and holes. If we put an external power source, the negative terminal of a DC battery, for example, on the n-type material, the phosphorus-coated surface, and we put the positive side of that battery on the p-type material, the boron, we could actually overcome that intrinsic field that's set up by the charges on each side of the depletion region, and in fact inject holes and electrons to the point where they decrease the size of the depletion region and eventually led to current flow. But if we reverse that battery and put the positive side on the n-type material and the negative type on the positive material, we would actually bring holes and electrons out of the material, and it would widen this depletion zone and fairly effectively block any current flow. Now, when I say that these are semiconductor materials, when you have no current flow, you still have some very minor leakage currents, but by and large it serves as a pretty effective block to current flow. If we have a p-n junction semiconductor that supports current flow in one direction at one polarity and blocks the current flow in the other direction or other polarity, we would call that a diode. Now on the blocking side, if we increase it enough, we can cause current flow anyway. It's termed that it goes into avalanche, and this is the basis of the Zener effect, or the Zener diodes, when you break down a diode in the reverse direction. But many diodes exist that will handle several hundreds of volts in the reverse direction and current flow in the forward direction, or forward biased diode. So what I would like you to notice and remember is that when forward biasing a diode, you will notice and be able to measure a small voltage drop across the diode, usually a 0.6 to 0.7 volts. What is that? That is your voltage potential across the diode has put it into conduction, but it still has to overcome the effect of the intrinsic electrostatic field of the semiconductor junction. And so in current flow, you will note about a 0.6 or a 0.7 volt drop. Keep that in mind. Now let's take away our battery. And we don't have a battery. And we have our PN junction, which naturally formed as a function of the amount of doping that we had in each of the materials and their proximity, the thickness of the silicon crystal, and that establishes a natural PN junction that happens entirely by itself, simply by the combination of holes and electrons swimming around in the material and finding each other and satisfying each other's needs. An exchange of body fluids. We create a PN junction, and it has an intrinsic electrostatic field that can have an effect on the flow and the positioning of electrons and holes. And now we shine some sunlight on it. And sunlight is about 52% visible light and 42% infrared and a few percent ultraviolet. So we have a variety of frequencies. And that causes it to excite the atoms in the cell itself, to the point where the electrons in the outer valence band of some of the silicon atoms, and certainly some of the boron atoms, and certainly some of the phosphorus atoms, promotes the electron. It picks up energy and leaves the valence band and becomes a free electron in the conduction band, leaving a hole. Now, if that hole grabbed an electron from the adjacent atom, you would say the hole moved. And the electron is free to move as well. But this intrinsic electrostatic field has an effect on them. And it tends to push the negative electrons in the free conduction band across the depletion zone barrier and toward the negative terminal, or the surface of the solar cell, the N-type phosphorus semiconductor, and toward the contacts. Holes left by the electrons tend to also be affected by this field and grab electrons next to them, and they migrate in the opposite direction into the P-type material and toward the contacts in the P-type material. And all this is driven by this intrinsic electrostatic field set up by the depletion region, by the PN junction in this material. And so electrons will flow toward the contacts, and holes will flow toward the rear contacts. And if we measure across those contacts, we'll get a voltage potential. And guess what it will be? Oh, 0.6, 0.7 volts. Why would it be that? Because at that point, enough of the electrons have moved toward the negative contact, and enough of the holes have moved toward the positive contact to exactly be in equilibrium with the electrostatic field across the PN junction. And this is driven by the additional energy added to the atoms by their being struck, essentially, like a cue ball, with photons, packets that transfer their energy into the atoms and so allow the electrons to gain energy and leave the valence band, leaving behind a hole. This solar cell will do about 0.6 or 0.7 volts. If I made this solar cell the size of a football field, guess what the voltage would be? About 0.6 or 0.7 volts. It is a function of the level of doping and the thickness of the material, but you're not going to vary it very much. All solar cells are about 0.6 or 0.7 volts. However, current is the measurement of electrons through a conductor, and we found out earlier today, I think it's 6.24 times 10 to the 18th electrons in a coulomb, and if 1 coulomb passes a particular point in the circuit in 1 second, that is an ampere. And would you believe that most of these cells, this is a SunPower Maxion, if we short the terminals, it'll put out about 6.28 amps. Now then, we won't be measuring any voltage if we short it, but we will have current flow of 6.28 amps. If we do no current flow, our open circuit voltage on this particular SunPower Maxion cell is 0.687. Now that's because this is a 125 millimeter by 125 millimeter cell, 5 by 5 inches. And you get about 1/4 of an amp a square inch. So if we made this the size of a football field, it might do 500 amps. But by the way, it's still going to do it at 6.87 volts, or 0.687 volts. The voltage is never going to go up. In full sunlight, it's 0.687, and in full darkness, it's about 0. And that is what a solar cell is. If we take 60 of them and mount them to this flexible panel, we can put this on top of an RV, and 60 times 0.582 volts is about 35 volts. And the reason I mention that, as we said, that our voltage open circuit is 0.687, and our current short circuit is about 6.28 amps. But there is what we term a maximum power point. Power being voltage times current. Here's a test question. If we're open circuit at 0.687 volts and we have no amperes, how much power are we creating? That's right, goose eggs, nothing. If we had a short circuit and we were doing 6.28 amps at 0 volts, how much power have we produced? 0. We have to have the combination. And so we can fairly quickly determine on the curve between those two extremes where the peak amount is. We don't have to, it's on the spec sheets. And in this case, the maximum power point voltage is 0.582 volts. As we increase the current out, the voltage diminishes. And the maximum power point current, instead of 6.28 amps, would be 6.09. And that is the point of loading of that cell where we get the maximum power, which at 0.582 volts and 6.09 amps is about 3.55 watts. That is the process of taking photon packets and converting it into current flow at a very low voltage and very quietly and very effectively, and that will do it for some time. This is this SunPower Maxion cell, and it's about 22.49% efficient. And let's talk about that. If we put 85 of these cells in series, we would have 58.4 volts open circuit and 49.5 volts MPPT. See, when we put them in series, the voltages are additive. If we put them in parallel, the currents would be additive. It's kind of like batteries, we typically tend to try to get higher voltages because that's the low side of it. 0.5 volts isn't very much. If we take 85 of them, we're up to, at a maximum power point, 49.5 volts. Our current is still 6.08 amps, but that would give us a 300 watt panel, 96 of these cells. This particular panel has 60, and that's going to give us a 200 watt panel the same way. And so we arrange the individual solar cells on the panels, usually with a glass protectant, a anti-reflective coating, our contacts, and of course our 2 layers of silicon material, or let's take a really thin layer of silicon, and using advanced deposition techniques and heat, we can dope each side, one side with boron and one side with phosphorus. And when exposed to sunlight, and of course most of the sunlight is striking the N-type or phosphorus side, but some will get through pretty deep. In any event, all the holes go toward the back, all the electrons go to the front, and they do that driven. The photons will knock an electron out of an atom and leave a hole, but it'll go right back in too, and that's called recombination. But with the sufficient p-n junction electrostatic field, we can get enough of these to migrate towards the contacts to have a voltage about the function of the electrostatic field. And if we put enough of them in series, we've got a considerable voltage. If we put enough panels in series, and typically they limit that to about 600 volts for certain pragmatic reasons, but we can do that. You can put strings in parallel to increase the current, and you can string them in series, the panels, to get higher voltages. Our play array, I call it. It's not our production array. We have 25 kilowatts on the roof on this side. It's actually tied in with the grid and produces power. And then I've got 13.5 kilowatts of Panasonic HIT panels on the other side. And I'll put up the spec sheet for these here on the wall. This is a 325 watt panel. It has a maximum power point voltage of 57.6 volts and maximum power point current of 5.65 amps, and that makes about 325 watts. You can string them in series up to 600 volts, and what we've done is put I think 8 of them in series for about 480 volts maximum power point, and 5 of those strings in parallel for between 25 and 30 amperes. And we use that array to play with charge controllers, batteries, vehicle controllers, and so forth, because it gives Bill the feeling of using the solar panels directly to charge the vehicles on sunlight. From Jack's perspective, the other side of the camp, the 25 kilowatts that we bring down, make AC, put it into the grid, use it to run the air conditioning, but we also use it to charge cars. That's charging from sunshine too, in my way of thinking. But to me, energy is just energy, and we're constantly increasing the voltage, decreasing the voltage, going from DC to AC, going from AC to DC, storing it in batteries, taking it out of batteries. It's all watts, coin of the realm, energy. But I did want to talk a little bit about how a photovoltaic array actually works, and some of the things you're going to hear when configuring your photovoltaic array is about what voltage you want, what current you want in full sunlight. The efficiency assumes a 1,000 watts, which is somewhat arbitrary. As I said, incident insolation of solar radiation on the Earth is 1,347 watts per square meter in direct sunlight. It's never direct. There's always atmosphere, clouds, various things, refraction, reflection, about 1150 at the Earth's surface. But for test purposes, they use a round figure of 1,000. And so in full sunlight, if you measure 300 watts, you're about, per square meter, you're about 30% efficient, which would be remarkable. Typically, you have a 300 watt panel today would be about 1.35 square meters of cell area. And in the case of the SunPower Maxion, 125 millimeter cell, that's about 22.5% efficient. In the case of the Panasonic HIT, it's about 19.7% efficient. Going into the future, they have multiple PN junction solar cells now, and using some different doping materials such as germanium and cadmium and all sorts of things. In the laboratory, the peak we've seen is about 46%, and that's where we can look in the future toward increased efficiencies. But again, it's kind of like the better battery thing. At what point do you quit paying for it? You know, if a panel's 20% efficient at X dollars and it's 35% efficient at, you know, a multiple of that, you know, you kind of have to find your pain level there, depending on how much roof real estate you have to play with, as to what you want to pay for the panels. So we really like the Panasonic HITs. They're very durable and reasonably priced at a good efficiency. Rena Solar has a pretty good 15.5% efficient panel that we have on our production side. These are actually made of the SunPower Maxions, and they're on a 3 millimeter lucite acetate type substructure with epoxy over the top of it. That's somewhat unusual. You would never put these on your house, and why are we paying extra to get that 22.49%? This is something you would use on a vehicle, and we sell them a lot to people with recreational vehicles and boats. Some cars, but because the material is lightweight and it's flexible, you can use adhesive to put it on the roof of a curved vehicle. It doesn't weigh very much. This whole thing's 6 pounds. And so it has some mechanical advantages, but the biggest thing is on the boat or the RV, we have a limited amount of real estate. And so we have to have high efficiency cells, and so we'll pay a little extra for that in that application, where we would never, you know, to get another 2 or 3%, I would not pay the SunPower prices when I can get good, very durable Panasonics at 19.7% at a much lower cost. For a rooftop, which I happen to have 14,500 square feet of rooftop, and so there's no shortage of real estate there. And so that's the photovoltaic panels. Let's go in the other room and talk about some of the other components of your home do-it-yourself solar installation to try to harness sunlight and put it in a car to drive. Stay with us. Just a quick section here. If you all will recall, we had a mystery of a Tesla motor that was a growler, and it was this rotor and its bearing, which had apparently prematurely eroded to become noisy. If you'll recall, we discussed down in here a bearing-like brush made of carbon fibers that rode on the axle and ostensibly grounded the axle and removed any induced currents, which several people have corrected me are not caused so much by the induced currents from the stator, but more by some inverter issues that cause currents to be induced into the shaft of the motor, and they're going to try to find their way to ground through the bearings and cause premature wear on the bearings. And so Tesla had put a brush that has fibers that ride on the shaft and ground it to diminish those currents and prevent it from going through the bearings. Well, I was quoting Tom Brunka of Hellwig brushes, because I know Tom, and I know Hellwig because they're the largest manufacturer of brushes for commutators that we used to use on the DC motors. Brushes generally are not what you think. They appear to be very simple devices, and it's one of those onions, as you peel it, it keeps peeling. We actually demonstrated a 3% increase in efficiency of a net gain motor based on using a different brush material that I can never explain to this day. And by the way, the manufacturer, Hellwig, cannot either. But we did it 3 or 4 times, and it came out the same way each time on the test. We went back and forth between these brushes, and it's simple. So brushes are kind of like EMI. It's dark magic, and I don't really like to go there. Apparently, since I was quoting Tom on the issue of induced currents in shafts, I may have left you with the impression that they made the brush in the Tesla motor and that it was failing. So they're suffering some umbrage at this misapprehension. I didn't really mean to give that impression. I didn't know who made the brush. I am assured by Tom that it was not Hellwig. They do know who it was. It was one of their competitors, and their brush doesn't do very good in his estimation, and not nearly as good as theirs. They were in contention to be in the Tesla and were not selected. And again, this gets to be a little bit of a complicated issue, and has really nothing to do with what's the best brush. You get into a lot of manufacturability issues, and as I understand it, to integrate the Hellwig brush in its most effective form would have required some significant recasting of the body of the motor. Well, the problem is there, when you get to moving that around, you fix one thing and cause 2 other problems that you thought would be okay, but then on the floor it turns out we've got another issue. And so they tend to be very conservative about making those sorts of casting changes, particularly on a device that's already in production. And so I think, but he does concur with my analysis of the bearing. It wasn't really axial forces. It's most likely induced shaft currents finding a path to ground through the bearing. And it is indeed an issue, but in this case it wasn't Hellwig's issue. and they spend a lot of. Hellwig is about an 80-year-old family-run company, kind of a small company that has stayed focused for 70 or 80 years, and they do a very good job at what they do, and they don't get off into a whole lot of other stuff. They kind of stay focused on their core thing, and I think they pretty much own commutator brushes for DC motors. They're never the cheapest solution, but they usually are the best, and so we've become friendly with them over time. As I understand it, they're in contention for the Model 3, but that's not really a determined thing either. Again, Hellwig tends to be pricey but effective, and of course there's always a temptation to spend less and hope for good things. That doesn't usually work out for me, but Tesla, give it your best shot, you know. But apparently the induced currents in the AC induction motor shaft, more a function of the inverter, as it turns out, is very real. And but these were not Hellwig brushes, and he did want me to mention that, so I did. Let's return to the topic of Tesla Model S batteries. Been studying on them a little bit. Found a whole group down in Florida that is wanting something to control these, and a number of people across the land. I would guess for everybody building an electric vehicle at home, there's about 1,000 guys working on home solar. Tesla has gone into an interesting marketing phase. They announced the availability of their Model 3, and I signed up for 2 of them and put down a deposit. In January, they announced the availability of the Powerwall, and I put a deposit down on one of those and ordered one. And this past month, they announced the availability of the solar tiles, and I signed up for that too. Thus far, they haven't sent me anything, and I don't think they have any intention of doing so. They're simply surveying people, taking deposits, and raising money on the secondary IPO market, bond market, leaving us somewhat on our own. A lot of guys are trying to do the Powerwall, and so we have taken on, because of a couple of disastrous fires and mishaps with these batteries, it's caught my undivided attention, which you probably didn't want to do, but we're there now, and by far and away, my interest would be in using a full Tesla battery pack, both for solar and for a vehicle. It's hard to get in a vehicle. However, my Cadillac Escalade has blown a transmission, and we've taken a look at this. Let's take a look at what we found. This is my beloved, if a little dusty, 2008 Cadillac Escalade. Recall, if you will, we put a dual DC 11-inch motor in this and a bunch of 400 amp hour Thunder Sky cells. And we've driven it since 2012. This is 2017. We did have the transmission go out along the way, and about 3 weeks ago we had the transmission go out for a second time. All along we had this monstrous DC motor with no regenerative braking and an automatic transmission that would slip and slide, and it more or less worked, but we went through a transmission every 2 years, and I would say that this has been a grand experiment in using an electric motor with an automatic transmission, and at this point I would rate it a fail. It works fine, but it doesn't work very long. The very quick action of the electric motor in going from 0 to full torque is just not a good match for a transmission that has, in Darwinian fashion, evolved with the internal combustion engine. And the bottom line is you will eventually tear up the transmission. I'm not going to replace the transmission again. We have better eggs to fry and chickens to lay. Let me show you something in the back that Bill set up that I think is quite interesting. Okay, we're back here with Bill Bayer. Bill has removed 54 400 amp hour Thunder Sky cells from the back of the custom battery box that we had built just for that purpose. And he was playing around this morning and put in 4 of the Tesla Model S modules. And side to side, what do you think you've got there to spare?
It's like about 2 inches.
2 inches to spare.
Give or take.
And if you set them end to end, slide one this way.
Just over an inch, not quite 2 inches, but about
not quite 2 inches. This is almost a perfect fit for 8 cells.
It's how I would do it.
If we were going to build the box to hold 16 cells,
I wouldn't make it
16 modules.
Nope.
It would be this size box, and this was built in 2010 for Thunder Sky 400 amp hour cells. Now, the Tesla modules are 75 millimeters thick, about 3 inches, a little under 3 inches. And not only could we get 2 layers, we could get 3 layers of them in here, but putting 2 layers of them, we'll have the full 16 modules, 85 kilowatt pack from the Tesla Model S in the back of the Cadillac Escalade. An 85 kilowatt pack, and room left over for our Tesla battery module controller, a charger, probably a DC to DC converter, really the whole gig. I have talked to a fellow named Mark Butgerite in Alabaster, Alabama, that does Impressive Creations, I think, is the name of their sort of West Coast hot rod type, custom car factory. What are you saying? Anyway, Mark has agreed to come get the Tesla Model S and to put a Tesla Model, come get the Chevy Escalade, take it down to Alabama, fabricate a mountain suspension system for a Tesla Model S full subclip under the Escalade. As I say, I like the Escalade. It's a big truck. It's easy for me to get in and out. I like the air conditioning and the heat, but I never really did like the way it drove with that automatic transmission. And after riding in the Doka, I want a Tesla-powered Escalade. So he's going to put the subclip under. What I want you to do, Bill, is take this box out, and we're going to set it up in the back of the Doka.
All right.
And we will test it on the Doka while this is in Alabama and get extreme range out of the Doka and get it all working. And when the truck gets back, we will simply transplant that box right back into position, but this time with 16 Tesla battery modules and our battery module controller, and see if we can make a Cadillac Escalade with a couple 100-mile range and a Tesla Model S drive unit in it. And I'll just keep driving this Escalade, but we won't be changing that transmission anymore. And so it would appear then I can rather easily not only get 16 Tesla battery modules in the back of the Escalade, but cut my battery weight in half in doing so and increase my range. And so we're going to embark on a program to convert the 2008 Cadillac Escalade to a Tesla drive unit, which has worked out surprisingly well on the Doka, and put a full Tesla battery pack in it. Unfortunately, we can't mount the slab, but by laying 8 cells down, 8 modules down, and another 8 on top of that, we can get all 16 modules in there and get a full 360 volt pack nominally charged to 403 volts and have an 85 kilowatt battery pack in a Cadillac Escalade. I'm also working on procuring a charger and a charge controller from China. And of course, we continue to work on our controller for the main Tesla battery pack. And all that's going to happen. That'll be how I power things around here with regards to solar battery backup and make my own power wall. Thank you, Elon Musk. But in the meantime, most people are dealing with somewhat smaller systems for their home. And as it turns out, 4 of these Tesla battery modules makes a very nice 20 kilowatt hour pack at about 48 volts. It's a little lower than most of the 48 volt systems as far as voltage, but it sure makes up for them in price, size, and weight. So we put together 4 of these modules. As it turns out, our 76 millimeter battery strap is ideal for connecting to my adjacent modules. So we did that twice and stacked them. And Dylan made me a nice copper bar shaped like a U, simply measured and bent with holes in it, and we connected the 2 ends of it together. This is going to be our EVTV controller for the Tesla Model S battery modules. And we've got that in a pretty small box, kind of a rat's nest of wiring, but it's coming along very nicely with some software and some other things to make a very nice controller to manage these battery packs and communicate with the BMS boards that were on here. If you will recall, Colin Kidder and I and a guy named Jared Tuma worked out the how to talk to the BMS boards and get them to balance cells. We can get voltages from them, and we can get temperatures from temperature sensors that are in each terminal of each of the batteries. The heart of how we did this, or the brains of the controller box, is of course our EVTV DUI. This is simply an Arduino DUI 84 megahertz that we took off one of the USB ports and added an EEPROM so we can save stuff, and a USB CAN port, a control area network port, CAN. To talk to the BMS boards, though, we had to do some level shifting, so we had to make a shield, and the more we chew on it, the more we make. Its basic purpose is to provide additional 5-volt power to power the boards, and to provide serial communications at a very odd data rate of 612.5 kbps to a 5-volt system that is daisy chained in a cable from one board to the next. And it has a connector on the end that brings out a lot of signals, those serial signals, the power, but also some, we've added 4 digital outputs with MOSFETs. Actually 8 of them, 4 outputs, 8 MOSFETs, so we can switch it one of 2 ways. We can either set it as a switch ground or set it as a switch 12 volts. Either way, it'll carry about 4 amperes, and that's more than enough to energize some contactors. This is the Gigavac GX14 contactor that we use a lot here at EVTV with electric vehicles. It can do a continuous 350 amps. In an EV, we don't care about that very much. We might do 1,000 amps, but we're not going to do it for very long. And so our average duty cycle on these things is 75 or 100 amperes, and often not even that. In this solar application, we really do need it to carry 350 amps continuously in some operations. And so that gives us our switches. We put 2 of these in here. We connect to the positive and negative terminal of this 2P 48 volt pack, which gives us 20 kilowatt hours and nominally 48 volts. And that goes into the box through the contactors and out to our terminal bars there. That gave us the opportunity to do a number of things. Most notably, we can pre-charge. We have a pre-charge resistor across the terminals of the positive contactor, and so we'll turn on the negative contactor when we want to energize the system and pre-charge through that resistor into whatever capacitive load we have for an inverter or for another device. We can set the pre-charge period in seconds to anything we want. And after that elapses, we close the positive contactor and are in full operation. More importantly, it lets us set in software some configurable limits on the temperature of those terminal sensors, a high voltage limit on the pack itself, a low voltage limit on the pack itself. We've added a variance limit where you can set, I've got it set to 0.2 volts now, where if any of the essentially 24 cells in this pack, we can measure the difference between the highest and the lowest. And if that difference exceeds our variance, we probably got a cell going bad. And so we will disconnect the box. So a lot of it's about control. We do have a couple of other things here. One is this connector allows us to bring out our power and control signals out of the box, and we do that with this connector. Of course, I've never met a connector I liked, but this happens to be the connector used on the Tesla Model S drive unit, so we had some of them laying around. And so that's our connector. We can make a harness, and I have one here somewhere for 2 of these modules, or for 4, or for any number really. In fact, our software and our scheme for this system allows us to automatically detect and to employ up to 63 of these individual modules. And that can make quite a large battery pack. On the other end, we have our 2 cables coming out. We also have a USB port to hook up a laptop to do the configuration, or to monitor a whole lot of data we put on screen about the pack that you don't normally have to operate. You simply let the box do it, but if you want to configure it or you want to monitor it, you can do it through the USB port. We have adopted these little 3.5 millimeter jacks. Just common stereo audio cables, not the 4-segment like Apple uses, but the old 3-segment stereo audio cable to carry CAN and our charge enable output. More on that in a minute. And so we can bring CAN out of the box and use it to communicate with other devices. Here on our bench, we've got 2 battery terminal blocks. We're going to connect a variety of equipment to this battery pack. The first one is a Magnasign 4048, I think it is. This is a great little inverter. I love this thing. It puts out 5,000 watts without breathing hard, and it's tiny. It's become the darling of the recreational vehicle crowd. The RV guys use these things constantly. You can plug in shore power, AC, and use that. It'll charge the battery at like 100 amps. It's a great charger, and then it'll pass through the AC to your house circuits on your RV. If you unplug shore power, then you can use the battery to provide 240 volts AC or 120 volts AC as you like, 60 hertz, up to 5 kilowatts. The next one down the bench, the big yellow one, is called the Sunny Island and Sunny Boy, and it is to a 5 kilowatt inverter. It does just 120 volts AC. If you want 240, you need 2 of them. But it is quite able to set up to use lithium batteries, and but it wants to communicate over CAN with a BMS. And so we've included code in our software to support the Sunny Boy. Outback Power is coming out with a great little unit this summer called the Skybox that will also be a charger, an inverter, and a charge controller for solar, and provide 240 volts AC at 5 kilowatts. And we're anxiously awaiting the release of that, and we're going to try to do whatever we have to incorporate that in here. We also have a charge controller on the wall, and I fall in love with this thing. Let's take a look. We got a little segment just on there. Okay. We bring our 5 strings of 8 Panasonic HIT cells in across the room here into an electrical panel we're using as a combiner box. There are combiner boxes available, and you should use the appropriate DC circuit breakers. We don't use circuit breakers very much. They're really switches, but we're combining 5 strings of 5.6 amps at about 480 volts into 480 volts and 25 to 30 amps, and we use it down there with our other charge controller into our original solar battery. But now we're playing with Tesla battery modules, and I found a charge controller that I really like. It's called the Morningstar, is the manufacturer. TriStar MPPT 600. The reason I like it is most of these charge controllers don't work for us. They have a maximum MPPT voltage of 100 or 150 volts. And then they're typically for 12, 24, 36 or 48 volt outputs. This one has an extremely wide input range of 100 to 600 volts. So it'll do an enormous variety of solar configurations. And it has a fairly broad output of 16 to 72 volts on the output to your battery. This is your solar battery charger. And it's a little bit different from most battery chargers in a couple of ways. Both are switching power supplies. A switching power supply uses some sort of a switching mechanism, typically a MOSFET or an IGBT, to switch your input voltage through a coil, an inductor. And that causes, as current goes through it, the buildup of a magnetic field. And then we turn off the switch, and the field collapses. But because the switch is off, it can't go back to the source. And we have a diode, because the polarity has instantly reversed on the inductor, and we let it discharge into an output capacitor. And it'll be a different voltage and a different polarity, an opposite polarity to our input. This is a common switching power supply, and it's how you use to step up or step down DC voltages. And you see switching power supplies all the time. In fact, most power supplies are now switching power supplies. However, they measure the voltage and the current on the output and rate the power supplies based on their ability to regulate very closely that output voltage and current. An MPPT charge controller is almost exactly the opposite. We don't care a whole lot what the output is. It's going to be about the battery voltage, or a little higher actually, so we can charge the battery. What we care about is the input. And that we can, on the regular power supplies, you vary the output, you get a higher voltage or more current by increasing the pulse width of the switching time or the frequency of the switching. And you can decrease it by narrowing the pulse width or decreasing the frequency. And so it's a very controllable output. In this case, we want to control the input. Recall in our discussion of the photovoltaic panels the concept of a maximum power point. That voltage or that current flow at which our voltage is maximum and our current is maximum, and the product of those two is the maximum power point. Now that's going to vary with the amount of sunlight falling on the photovoltaic arrays, and all day long the sun's in motion and we have clouds moving around, birds shitting on things, it just never ends. So it's a variable moving target. What this device does, and all MPPT charge controllers do, is seek the maximum power point. Not only can we change the frequency and the pulse width of this switching power supply, but we could do it 100 times a second. And in fact, we can do it, take a measurement of what the input voltage and current is, change the pulse width, and measure it again, and change the pulse width and measure it again, and do our main charge point and 5 points either side of it continuously. And if one of those gives us a higher power, we simply slide our pulse width and or frequency towards, and it's really pulse width, towards that point. And so we're continuously changing the pulse width to try to keep the maximum voltage and current point at which we get the maximum power out of the solar panels. And we kind of let that go to the batteries, and the voltage we're applying may vary somewhat. But the concept is to track the power out of the solar panel. This one does it across a very wide range, 100 to 600 volts. That's unusual. And across a quite wide range of battery outputs, 16 to 72 volts. And you pay for that flexibility. This little puppy's about $1,489, where you can pick up charge controllers for as little as 40 or 50 bucks in a very low power range. This one will do about 3,000 watts. So we can be doing 50 or 60 amps here pretty easily, which is a lot. More importantly, across a wide area. Above it, where we actually have run in our 460 volts, 25 or 30 amps using just some basic 12-aught Romex, the 20 feet that we're going to carry that small amount of current. We have used a GigaVac mini tactor. This is a small contactor that can do 800 volts and 35 amps, and we're not going to have more than about 25 amps, and we can turn that on and off. I have connected the coils to a 3.5 millimeter audio jack stereo cable, and that just plugs in. And if we had 12 volts on the tip and ground on the ring, or 12 volts on the ring and ground on the tip, that contactor would energize and apply our solar power to our charge controller. We're going to use the charge enable output of our EVTV module controller to turn this on and off, and we're not even going to have to fool with the charge points. We'll just set the maximum on the TriStar and use our controller to determine whether it's charging or not. Stay with us, there's more to come. And so our Morningstar charge controller can do up to 60 amps charging this battery. The big thing is it has a very wide voltage range that it supports for batteries for the charging, but it also has a very wide input range for the solar photovoltaics. Most of the 48 volt charge controllers have a maximum PV input of 100 or 150 volts. This one will go up to 600. And 600 is kind of a magic number. Most of the panels are made to be in series up to 600 volts. And so that thing is pricey. I think it's about $1,489, but I've fallen in love with it already, as you'll see. Again, the voltage of the Tesla Model S battery is not precisely ideal. Nominally 3.6 volts. We charge them to 4.2 volts, and their life is pretty much over at 3 volts. When we have one pack here, that's about 21.6 volts nominally. It's going to go out at 18, and we're going to be kind of charged up at 24 volts. Most of the solar equipment runs on, or is designed for 48 volts, runs from 41 or 42 volts up to as high as 64. Well, we'd be burned up at 64. Never mind all the goofy arrays and switches and so forth they have for that. So what we've done is provided one of those digital outputs from our shield. We can switch 12 volts onto that, put it on a 3.5 millimeter jack with a return, and I can use that to control one of our little 35 amp mini tactors from GigaVac and switch the solar power on and off to the charge controller. In that way, when we get up to our cutoff voltage, also a configurable item, we can simply cut off the charge enable signal coming out that jack, de-energize that contactor, remove all the solar power from the device. If you were going to have more than one string or two strings, the Morningstar will do about 3,000 watts. If you need more, you could do them in parallel. You'd use that charge enable to switch a little Bosch relay to energize each of the solar inputs separately and each of the Morningstars separately. And that would work out pretty well. And then we have our CAN port. We can provide CAN to the Sunny Island inverter to interoperate with that. But we've kind of invented a battery management protocol. That protocol will let you do up to, I think, 15 batteries, 63 modules each, up to 255 cells per module, in kind of a universal 29-bit message addressing scheme to very flexibly deal with batteries, modules, and cells in a very large system. 15 batteries of 63 modules of these 6 cells would be about 860 Tesla Model S battery modules and about 4.4 megawatt hours of storage. But you would be able to manage all that from one device using this proposed protocol for large-scale battery management systems using 29-bit addressing. The operation of this, we want it to be deep with a lot of things that you can control, but the basic operation is pretty simple. I press this power button here, and there is my negative contactor coming on with a red light, and after my pre-charge delay, there is my green light coming on indicating the positive contactors connected. And actually, I happen to know that we've also turned on the charge enable. Our Morningstar is already charging this at somewhere between 39 and 60 amps while we speak. I could, while it's charging, reach over and trip on the magnesign, and I actually plug that into a 220 plug here in this room and switch off the 200 amp service to the top of the circuit breaker panel and power everything in here off of this battery and that converter. It's just in this room. I've got other panels in the other rooms and so forth, but all the lights, refrigerators, fans going on today because of the heat, we can power and have powered with this magnesign. So we think this controller will be the key to safely interacting with 4 of these modules for a small scale solar system, or 16 of them in an Escalade. And since I can do CAN with it, we'll probably design some further integration with the Tesla drive unit to go back and forth there, and probably replace our little IVT current sensor and use this instead to have individual cell monitoring at the cell level for the vehicle. So it's a big area of development for us. We're also going to continue with the similar module for the main battery pack, but I wanted to do this this first because it's kind of the hardest to get all the software and hardware. We use a little LIM cab current sensor in there. We already have voltage, so I don't need the more expensive IVT current sensor that we use on the Tesla drive unit. But the LIM Cab 300 does a great job of measuring current bidirectionally, and with a really quite notable accuracy, add up to 400, 500 amperes, which is more than we're going to be able to do with this system, I would think, in a solar operation. So that gives us pretty much complete control. We can charge, discharge, balance, note variation, note temperature, just about anything you would want to do by way of knowledge about the batteries, but more importantly, unattended control, where if any of those limits that you have preset occur while you're upstairs in bed, this thing shuts down, and it shuts down right away, and it's off the charger, off the inverter, it's done. You have to come in, bring it back up with a laptop, figure out what the problem is, and address it before you can reconvene and reconnect it and make it work again. So that's our basic hardware. Let's take a look at what some of the software I've got put together is doing for this. All right, we're going to take a look at the software running the system here for our EVTV controller. We're going to bring up a cool term. I'm going to go to options. I'm going to try to find a USB connection here. We'll have to plug it in and rescan the serial ports. And I have USB modem 1421. I'm going to go to 115,200. I'm at 8 data bits, no parity, 1 stop bit. All that looks good. I'm going to go to my terminal and go to line mode. Enter key emulation as carriage return the line feed. You have to have that to enter commands. And I use a form feed in my code just to kind of keep a clear screen that I update quite a bit. And so we've set our connection. I'm going to connect, and here we have our EVTV Tesla battery module monitor version 1.08. In that title line, we give our runtime in days, hours, minutes, and seconds. We've been up about 5 minutes. It scans the pack. Now we can have from 1 to 63 modules, and it will find them. This is the pack status. This is faults of all the modules. Right now we have no faults. We have discovered 4 modules, and we have a combined battery voltage of 48.82 volts. More on that later. An average cell voltage of 4.09, and an average terminal temperature of 32.27 degrees centigrade. Then we have this bank of 4 modules here. Now understand that's because we're connected to 4 modules. If we were connected to 8 modules, you would have a longer printout here of 8 modules, or 16, or up to 63, which would make a long screen. You'd have to scroll back and forth to see things. First thing we show is the voltage for the module itself. Here is 24.41 volts. And then we have 2 temperatures. The first is your negative terminal temperature at 32.10, and your positive terminal at 31.9 degrees centigrade. And then we have our 6 cells and their individual voltages. And we do that for each module. Then we show our battery state of charge. I can zero that out to 100 here by entering a Z command. Our current is a minus 13.9 amperes or thereabouts. That's actually a function both of our solar charger and our Magnum power inverter. going on at the same time. Discharge is shown as a negative current, and charge would be shown as a positive current. We're adding amperes or amp hours to the battery would be positive, or we're discharging, taking them out as a negative. That is a power of 670 watts. That's that instantaneous current times this instantaneous pack voltage will give us our power in watts. And again, negative powers are discharge. And this is watt hours. This is the number of watt hours that have been discharged in this amount of time, 8 minutes and 12 seconds here. Our battery capacity is a configurable item. It's 410 amp hours. And our current amp hours this session is minus 0.34 amp hours. The battery state of charge is a function of the number of amp hours since it was last zeroed, and that is persistent from one session to the next, divided by our battery capacity that we configure, and that's how we calculate state of charge. So this amp hours is persistent in the EEPROM, whether we're powered up or not powered up or whatever. It will continue to accrue, and it'll go in both directions. It'll go negative when we're discharging and positive when we're charging until we manually zero it out. In operation, as you discharge, of course, this will get to be a higher negative. But then when you charge solar, when you're not using so much electricity, it will reverse and decrease back in a positive direction. This is an interesting line here, battery lifetime charging and discharging. You can't zero these out at all. This is like an odometer. And we have to recompile the software to change this. We'll send it to you zeroed out. But it will accrue all of the energy that you charge and all that you discharge separately and ad infinitum. As long as you run the system, and whether it's on or off, these numbers will keep growing as you use the system. And that lets you get some indication of how much energy you've had in and out of your pack over the time of ownership. Max system discharge current is minus 96.43 amps. You can see that right now we're at about 13 amps discharge, but when we first engaged the contactors, it jumped up to 96 amps. That's not too bad. It would indicate to me that maybe we need a little longer pre-charge time. This prototype unit has a 500 ohm pre-charge resistor. That's a little high for a 48 volt system. We'll probably go to 50 ohms and 50 watts in our pre-charge resistor for the production unit. But this is an instantaneous value that's updated every time we read current. If we have a higher current, that would replace this. So it's a peak snapshot in time of the highest value we've gotten. And here's the highest value we've gotten for charge in this session. Out of all these cells here, this is the highest cell voltage, and this is the lowest cell voltage, to keep you from having to read through all these to find them. It just tells you what the high and low voltage is. This is our negative contactor is on. Our positive contactor is on. Our temperature alarm is off. That's set by two values, high and low, before temperature. Our voltage alarm is off, and that's, again, a high volt and a low volt that you set at the cell level. We don't care what your pack voltage is. We don't care how many cells or modules you have. What is the highest voltage any cell can reach before you basically throw the alarm. If either of these alarms are thrown, these contactors are shut off and the system's disengaged. This is our charging enable output. It's on, and it's a function of two values, cut off and resume. Cut off is the voltage at which we simply command all charging to cease. And you lose your 12 volt output for charging enable. Resume is if your battery pack then falls to some lower level and you set it, that's where it would start charging again. If you haven't set to the same thing, of course, it's going to hit it, cut off the charging, the voltage will fall immediately, it'll come on immediately, it'll immediately charge up and exceed it again, and it would simply sit there and chatter. But by having a cut off and a resume, you can say cut it off at 4.2 volts per cell and have it come back on at 3.8 or 3.9. And so you can use the system for a while, use some energy out of it before the charging comes on. It keeps it from jumping back and forth. So where do all these configuration items come from? Let's enter a question mark, and we get another screen. Our configuration menu. Again, you have to terminate any commands with a line, feed, a carriage return, or both. We can set our can speed. You simply enter can speed equals 250, let's say. And it doesn't care if it's uppercase or lowercase. You can enter 250 or you can enter 250,000. It doesn't care. And let's see here. There we go. We're at 250,000. I can also simply say can equals 500. And we're back to 500,000. Note I just entered the first three characters of this command. So far we've been able to have all our commands where you can enter the whole command or you can enter the first three characters. It doesn't care. Battery ID. I recall we were talking about a protocol. We can have up to 14 controllers, each controlling up to 63 modules. And each module can have up to 255 cells. In the case of the Tesla Model S, of course, they have 6, and that's it. But this is for our CAN protocol to manage large numbers of these things together. So I guess 14 of them, and each of them up to 63 modules. So normally we'd be battery ID number 1, but if we had 2 of these controllers online, we'd have one to be 1 and one to be 2. That's how we keep them straight. Have some single character commands. Clear all module faults. If you recall back here, pack status no faults. Well, sometimes faults come up, and this is where you can clear them and see if they pop back up. If they do, you probably have a problem. Display internal resistance screen. I'm going to talk about that later. S is search for connected modules. We simply search for connected modules. Actually, that occurs every time we power up the software. We seek them out and reassign IDs and renumber them every time we apply power coming up. So you can simply take your controller offline with the power switch, add 2 more modules if you want, and you're up to a 30K 48 volt pack, and when you power it back up, it already knows that by the time it's painting the menu. But this is a way to manually search for connected modules. Reset original internal resistance record. I'm going to talk about that a little bit later too. Z resets state of charge values to 100%, currently at 99.51. That's an important command. Normally you'll charge and recharge and it'll wander around in a solar application. Once in a while you need to bring it up to full charge and zero it because there are losses in the system both ways. And that'll get you back to sort of synchronizing. So this would be a fairly often occurrence. You might plug in and bring it up to full charge and zero out your amp hours and state of charge. Just resets it. O clears the alarms and cycles the contactors. If you trip an alarm, you can enter an O, and it will clear your high volt alarm and your high volt alarm and cycle it. It'll probably trip it again. You can then change the values down here and bring it up to see what's actually going on, but you don't want to give up on your limits. Capacity equals 410. I could enter a command cap equals 415 here, 0.22, and as you can see, there it is. We just changed our capacity, and our state of charge actually changed because of that. Let's put that back to cap equals 410. That is really, we're using the 64 cell modules out of a 60 kilowatt pack, and it's really only 205 amp hours per module. The 74s are about 235 amp hours per module, and we have two of them in parallel, and so that gives us 410 amp hours of storage. Parallel equals 2. This is actually kind of a important value. Recall that I said we had 48 volts. We actually sum all the modules, and so we're measuring 96 volts, and we'll divide that by pretty much whatever you want, and this allows you to configure your things. We'll determine the number in series. We know how many modules we found, and if you'll tell us how many strings are in parallel, we can work out how many are in series. This is a 2S, 2P pack, but we can figure out the 2S if you give us the 2P, and then that tells us how to calculate your high total pack voltage. Pre-charge is 6.50. That's simply seconds. Enter how many seconds you want it to do on the pre-charge, and that'll work. High voltage is the highest voltage, highest cell voltage limit for contactor cutoff. Now, this is not to stop charging. This is where you determine, hey, we've got a problem. Something's gone wrong. We're being overcharged. We're going to disconnect the system. We're throwing an alarm and we're disconnecting the system. We would advise the Sunny Boy that we have an alarm before we do that, but not very much before. Low voltage is the same. At this voltage. Now understand, when you're under a load of 100 amps or so, you may go a little bit lower than a static voltage might. But you can learn by experience what that is as your battery pack depletes. Variance is very important. That's the maximum allowable difference between cell voltages, and that is from the highest cell to the lowest cell. I've got that set to 0.25 volts. If one cell starts to get much higher than the other ones or much lower, that's a sign of a failing cell, and we're going to catch that before it becomes a fire. And so have fairly conservative limits on that, what you'll allow. High temperature is the high temp limit for contactor shutoff. Low temp is, I've got set for 5 degrees. Let's talk about low temp for a second. We can go to minus 20 degrees Celsius to operate this battery. We don't ever want to charge below 0. And that's because it actually damages the cell. Now, these are temperatures as measured at the terminals of the battery modules. Not what's outside, but whatever those terminals are, that's what we take as the temperature. I've actually hard-coded it in here that your charge enable will cut off at 5 degrees centigrade. You cannot charge below 5 degrees centigrade using the charge enable output. If you're relying on some other device to determine your charge when it comes on and comes off, like your inverter or your charge controller, and I don't recommend that. But if you do, set this low temperature to 0 degrees centigrade at the lowest, and make sure you disconnect the pack and do not allow it to be charged below 0 degrees. It causes lithium plating on the anode, and it is destructive to the cell. Cutoff is 4.20. If our highest measured cell voltage hits this value, the charge enable output is disabled. In the case of our midnight charge controller, that would disconnect the solar power from the controller, and we simply can't charge past that. Resume, I've got set to 4.0 here. That doesn't make a lot of sense. Let's say resume equals 3.85 volts. And there we go. This shows that our negative contact is on and positive contact is on. And a question mark to return to our monitor screen. I'm going to enter an I to display our internal resistance screen. This calculates an internal resistance for each and every cell in the pack. I'm not real happy with this. I don't know if this will make it into the production version. I thought I'd play with it. The concept is that by measuring internal resistance and comparing it to what we had when we put the pack in service, that we can detect deteriorating cells. Here's the problem. I've got this set where I take the voltage of the cell anytime that it's under 15 amperes, and I store it in an array along with the current that was being discharged at that time. I don't take any samples while charging, only when discharging. And if it's more than 20 amps discharge, I take that for a high value of current, and I save the voltage there, which should be some less because of the discharge. And then I can calculate the change in voltage for the change in current. unfortunately, for this pack, that winds up being a very low value. And here's why. The individual cells might have an internal resistance of 60 or 70 milliohms, but we don't have individual battery cells. We have voltage cells that are made up of 64 of those batteries. And in the case of an 85 kilowatt pack, 74. Those 74 cells have the capacity to put out 1155 amps in a P85D. And actually, using the same cells, they'll go up to 1350 amps briefly in like some of the newer models. That's a lot of current. We're not in a 48. If we went 300 amps at 48 volts, we're at 16 kilowatts. Now that's nothing for a motor, but it's a shit pot of power for a house, even for a big house. You just rarely see backup generators above 15 kilowatts because there's just no need. You can have 5 air conditioners coming on at the same time, and it would still do it. So we're not going to see currents much above 300 amps, and while I'm sitting here discharging 15 or 30 amps, this is not going to make much sense. My hope is that over time, and with increased loads, that it might. And then if I enter an R, I simply just copied the instantaneous values into EEPROM. And that'll be displayed as the original internal resistance for the rest of creation, or until I hit R again. So this lets you take a sample of an internal resistance using some realistic currents for your system, and then save it to the EEPROM, so you can go back later and get current internal resistances and compare them to what you had originally measured some months back. I think simply because of the massive number of these 18650 cells in parallel, and their very high collective power output, that at 300 amps, we're going to load it sufficiently to do anything particularly accurate with internal resistance. But if we did, it would be, you would run the system at some discharge level, but less than 15 amps for a few minutes, and then put it under a load of 300 amps or so, and that would give you about the maximum delta you're going to have in current, and so about the maximum delta you're going to have in voltage, and your best calculation for an internal resistance. I kind of suspect this is not going to be a very popular or useful item. We may work on that strategy over time. But that's our basic monitor thing. We've got a number of configuration items you can set, and right now we have our charge enable on. We're actually charging at 11 amps at the moment while we're running power in here. Now what I can do is set my cutoff equals 3.9, let's say. And that's going to shut off my charge enable output. And now we can see our true, we're no longer charging. This is our true discharge of 31 amperes into the Magnum power that's powering the room I'm in at the moment. And you can see that's putting out 1500 watts. We've got a couple of fans on, a refrigerator, a whole bunch of lights. Now we do tend to use LED lights, but still, it's everything in this end of the shop. And we're using 1500 watts from this little inverter that will only do 5 kilowatts. Well, 5 kilowatt, we can have both lifts going, a heater. It's you can do a lot with 5,000 watts, even from that little Magnum power unit, which is it's less than $2,200 retail. And so you can do a lot with this sort of a system. And of course, at 5 kilowatts on a 20 kilowatt pack. Now, I would say you're probably not going to get 20 kilowatts out of the pack, and here's why. Most of the devices cut you off at about 41 volts. Well, 41 volts is only about discharge to, say, a stated charge of 20 or 25%. We're not really discharged. We would be fully discharged at about 36 volts. And I can show you a little chart here showing the discharge curve of these batteries configured as a 48 volt pack. And you can see that, at 40 or 42 volts, we're in our prime here. We're not fully discharged. So you have to oversize your battery pack a little bit using these modules. That's actually not a bad strategy anyway, to never fully discharge your pack and to keep it on the top 2/3 of its operating range is actually good medicine in the solar installation and will maximize the life of your batteries. And so that's pretty much okay. But it is the one caveat when using the Tesla Model S cells. Their world in the inverters and their world in the charger controllers is based on the 2.1 volt lead acid cell. And you have 6 of them in a 12 volt battery, and you have 12 of them in a 24 volt, and you have 18 of them in a 36 volt, and you have 24 of them in a 48 volt. We're dealing with nominal 3.6 volt cells, and so 6 of them gives us about 21 volts nominally. 12 of them gives us about 42 nominally, and fully charged about 48. They typically charge the lead acids to 57, or with equalization as high as 64 volts. So we're a little bit slid down the range there a little bit from what they're accustomed to seeing. I think we can use this charge enable output to control that. Like say the Morningstar, I'll just leave it set where it'll charge to 60 volts or something, but we're not going to let it do that because we cut off the sunlight at our 4.2 volt per cell value. And so that's an overview of the EVTV controller for the Tesla Model S battery modules. We're going to use that as a battery pack for our own Tesla Powerwall, but I think we can do it for a little bit less money than we can a Tesla Powerwall, which is priced at I think $11,400 for 14 kilowatt hour. Well, this would be about 20 kilowatt hours, certainly 14 usable. We'll probably price this controller somewhere about the price of one module, $1,300 or so. You pick up 4 of the modules, you're at $5,000, $6,500 with a controller. um, 8,000 with the charge controller, but for 9,500 you could have that Outback combined charger and inverter on a 20 kilowatt system and be beating the game rather significantly. If you want to buy a battery out of salvage and take it apart yourself, you can beat that considerably. $1,345 price is on eBay. It's a guy that simply buys wrecks, takes the batteries out, pulls the modules, and sells them, and makes good money doing it. So one strategy is simply to buy full packs out of wrecks and disassemble them. Take your 4 modules and sell the other 12 to other people. And you'll probably wind up with a free battery pack that way. In any event, we've decoded how to read these. Oh, the battery balancing. Well, I've got that set up in here now, as I really only do it at the top end of the pack. It will, if any cell is above 3.6 volts, it'll go through the whole series of cells and find the highest one and turn on balancing. That's basically a little shunt. Drains about 125 milliamps, I think, across the terminals, kind of knocking it down, taking a little energy out of it. And then 4 seconds later, it does the same thing to the next highest, because the first one is being drained for 15 seconds. Some other one will be the next highest. One thing I failed to mention was balancing. The way balancing works is I only want to do it at the upper end of the pack, above 3.6 volts. But if that's going on, what it'll do is go through and find the highest cell and set a little tiny MOSFET to bleed across the cell about 125 to 200 milliamps across that cell for 15 seconds. And 4 seconds later, it will go find the next highest cell, because the first one has decreased in voltage. That typically would leave another cell as then the highest one. And it'll set that one to also discharge a minute amount of current. And 4 seconds later, it will select a third one, and then a fourth one. At that point, the first one will have terminated its discharge cycle, and it may again come up as the high cell. But whichever one comes up, and it will continue to do that until there is a variance of less than 0.015 volts from the highest to the lowest. And at that point, it simply quits balancing. And so it's really quite automatic. Colin had some things in there that you could set with hysteresis and balance voltage and so forth. I I guess I thought that was a little bit too manual. It's kind of a set thing. I've got a balance strategy that seems to work. As you can see, all these are pretty close. They were not when we started playing with this pack. It takes hours or days to bring them in balance, but they will come in balance, actually pretty nicely. And so the balancing algorithm we have works pretty well. When they get below 3.6 volts, I don't want to be draining material out of cells. I certainly don't want it to happen on the bottom end of the pack where we've disconnected from the system, but we're still bleeding cells down with balancing. That doesn't make much sense. So that's why that's the situation. Anyway, that's a rundown of our EVTV controller for Tesla Model S modules, battery modules, and I think it's a good start. We continue to work on the software. By the time we have these available in the web store, it may not look a whole lot like this, but this is the basic approach and the amount of information. The idea is that you be in control of the limits of your pack, and that we, in operation, you basically push the button and walk away, and it will do that. But if the light magically goes off and your battery pack isn't responding, you should be able to plug into the laptop and get all the information you need to figure out what's really going on here, and make repairs as necessary. That's the concept. The overarching mission is not to provide battery backup, but to disconnect battery backup. If everything isn't absolutely perfect. And so if you have too wide a variance in your cells, you have too high a voltage, you have too low a voltage, you have too high a temperature, you have too low of a temperature, its job is to disconnect this battery pack and prevent a fire. That's what it's about. You can, if you're tripping voltage temperature alarms and you get on here, you can see the temperature on the screen. You can watch it operate for a while, watch the temperature alarm go off. You may decide, those little nozzles on the back of those Tesla Model S pack, why don't we hook that up to a cooling system? And because the level we're using this battery pack at, it's generating heat. I would suspect that by far the majority of you, your use of the battery pack, it's never going to generate enough heat to be a problem at all. And so, but that can build up over hours. And so if you put on your pack and 10 hours later it trips and goes offline, and you fire it back up and it works fine, and 10 hours later it kicks out, it's easy enough to hook up a laptop and watch those temperatures climb over time, and you may decide that additional cooling is probably required. Stay with us.